Please pause the video and try this problem. And now let's discuss the problem. Here's a summary of the solution for the problem. Now let's discuss the solution step by step. For this problem, we will treat the motorcycle and its rider as a single combined object. After that combined object leaves the ramp, and before the combined object hits the ground, the only force on the combined object will be the force of the Earth's gravity. So, the combined object, which consists of the motorcycle and its rider, will undergo projectile motion. This problem is a symbolic problem rather than a numeric problem, because the problem gives us symbols to work with, v sub naught and h, rather than giving us numbers. For a symbolic problem, you should write down a list of the given symbols. A symbol that is explicitly mentioned in the problem is treated as a given. So for this problem, the symbols v sub naught and h are treated as givens. Now, the symbol capital D is also mentioned in the problem, but obviously the symbol capital D should not be treated as a given, because capital D represents what the question is asking us to determine. A symbol that is not explicitly mentioned in the problem is not treated as a given. But here's an exception. The symbol little g is treated as a given, even though little g was not mentioned in the problem, because little g represents a known physical constant, 9.8 meters per second squared. Remember to write down your list of given symbols. How will this list be helpful to us? Well, we can treat the given symbols as knowns. So, listing the givens will help us to identify which symbols in our equations stand for knowns and which symbols stand for unknowns. Also, only the symbols that are treated as givens should be included in our final answer. The general path for two-dimensional projectile motion is a parabola. Since the ramp is horizontal, for this problem, the path of motion will include only the right half of this parabola, like so. Since the ramp is horizontal, the slope of the parabolic path at time t0 should be horizontal. The slope at time t0 should not be upward, and the slope at time t0 should not be downward. The slope of the parabola immediately after time t0 should be downward. The slope of the parabola immediately after time t0 should not be horizontal. The problem tells us that the horizontal distance from the ramp traveled by the motorcycle is referred to as capital D. So we can represent what the question is asking us for with the symbol capital D. And we can build that question into the sketch like so. Let's call the instant when the motorcycle leaves the ramp t sub 0. And let's call the instant when the motorcycle hits the ground t sub 1. For projectile motion problems, it's usually best to choose up and right as your positive directions. So let's choose up and right as our positive axes. This is the furthest left position of the motorcycle during the interval of projectile motion. And this is the furthest down position of the motorcycle during the interval of projectile motion. So let's choose this point as our origin for measuring position. Write down the coordinates for position for each of the key points in time in your sketch, and try to write down a specific value or symbol for each coordinate, like so. The problem tells us that the position at time 1 is located at a horizontal distance of d to the right of the origin. So x1 equals d. So we can use this question mark to indicate that when we know x1, we will know the answer to the question. The problem tells us that when the motorcycle drives off the ramp at time 0, the motorcycle is moving with speed v sub naught. The object's speed at time 0 represents the magnitude of the velocity vector at time 0. So let's draw the velocity vector at time 0. The velocity vector at time 0 is drawn tangent to the motorcycle's path of motion at time 0. Tangent to the path of motion at time 0. Like so. At time 0, the motorcycle is leaving a horizontal ramp. So the slope of the parabolic path at time 0 is horizontal. So the velocity vector at time 0 is horizontal. Now we need to break this velocity vector into components. The velocity vector at time 0 is parallel to the x-axis, so we can use this rule to break the velocity vector at time 0 into components. The velocity vector points to the right, which is our positive x direction. So the x component of the velocity is positive. The x component has the same magnitude as the overall velocity, which the problem tells us to represent with the symbol v sub naught, written without an arrow on top. And the other component, the y component, is 0. Remember that it's a good idea to include a plus sign in front of a positive component. Let's label t sub 0 and t sub 1 as our initial and final points. Now we're ready to create the projectile motion setup, and then to work with the kinematics equations. Let's begin our projectile motion setup. In a projectile motion problem, the only force on the object is the force of the Earth's gravity. Gravity pulls down. So, in a projectile motion problem, the direction of the acceleration is down. And we chose down as our negative y direction. So, a sub y is negative. In projectile motion, the magnitude of the acceleration is equal to the constant little g, which is equal to 9.8 meters per second squared. Ordinarily, for a projectile motion problem, we would substitute the number 9.8 meters per second squared for the magnitude of a sub y. But since this problem is symbolic, we will use the symbol little g rather than using the number 9.8 meters per second squared. When we write the symbol little g without an arrow on top, that symbol stands specifically for the magnitude of the acceleration due to gravity. So it's crucial to include this negative sign to reflect that in a projectile motion problem, a sub y points down. By itself, the symbol little g would stand for a positive number. So if we want a sub y to be negative, we have to include this negative sign. In your setup, indicate the question with a question mark. We've determined that when we know x1, that will tell us the answer to the question. We're treating x1 as x final, so we put a question mark above x final in our setup. So our plan is to use the setup for the y component to determine delta t. Then we'll substitute our result for delta t into the kinematics equation for the x component. Then we'll use our equation for the x component to determine capital D. Based on the work we did in our sketch, we can substitute specific numbers and symbols for each variable in our setup, like so. Remember that the symbols on your list of givens should be treated as knowns. V sub naught, h, and little g are on our list of givens. So V sub naught, h, and little g should be treated as knowns. On the other hand, symbols that are not on your list of givens should be treated as unknowns. Capital D, delta t, and V sub 1y are not on our list of givens. So capital D, delta t, and V sub 1y should be treated as unknowns. Our x equation still has two unknowns, capital D and delta t, so we're not ready yet to solve the x equation. When you know 4 of the variables in your setup for the y component, you're ready to choose a kinematics equation for the y component. We do have 4 variables for the y component that we can treat as knowns: y initial, y final, v initial y, and a sub y. So we're ready to choose a kinematics equation for the y component. We care about these 4 variables because we're treating these 4 variables as knowns. And we care about delta t because we're planning to substitute our result for delta t into the kinematics equation for the x component. So for this problem, the kinematics variable that we don't particularly care about is v final y. So let's choose the kinematics equation that's missing v final y. That's this equation. Be careful to include this crucial negative sign when you substitute for a sub y. Remember that the symbols h and little g are treated as knowns because those two symbols are on our list of givens. So this equation has only one unknown, delta t. So we're ready now to solve this equation for delta t. We're trying to solve this equation for delta t. That means we need to get delta t by itself. That means that we need to separate this term from this term. One acceptable way to separate the terms is to move this term to the left side of the equation. But here's a more efficient approach. Instead of moving this term to the left side of the equation, let's move this term to the left side of the equation. This approach is more efficient because it allows us to separate the two terms and to eliminate this negative sign in the same step. Remember, we want to get delta t by itself. The next step in that process is to eliminate the 1/2 and the little g from the left side of the equation. The most efficient way to remove the 1/2 and the g from the left side of the equation is to multiply both sides of the equation by the reciprocal of 1/2, which is 2/1, and to multiply both sides of the equation by the reciprocal of g, which is 1/g. That allows us to cancel the 1/2 and the little g from the left side of the equation. Our result is that delta t equals the square root of 2h/g. We've used a kinematics equation for the y component to determine a result for delta t. Next, we substitute that result for delta t into the kinematics equation for the x component. We get the result that capital D equals v sub naught times the square root of 2h/g. Remember that our goal was to determine capital D. Now we're ready to answer the question. Our answer is that capital D equals v sub naught times the square root of 2h/g. For a symbolic problem, our final answer should contain only symbols that are included on our list of givens. The symbols v sub naught, h, and little g are all on our list of givens. So this answer does satisfy this requirement. For example, consider this possible answer to the question. Capital D equals v sub naught times delta t. Now, this is a true equation, as you can see here. Nevertheless, this would still be considered to be an incorrect answer to the problem because delta t is not on our list of given symbols. In order to get this correct answer for the problem, we had to substitute this expression for delta t, which involves only the given symbols. Now let's ask whether our results make sense. In particular, let's ask whether this equation makes sense. What happens if we increase v naught while holding the other givens constant? This equation implies that if we increase v naught, capital D will also increase. What would happen if we increase h while holding the other givens constant? h is on the top of this fraction. So if we increase h, that will increase the top of the fraction. Increasing the top of a fraction makes the fraction as a whole bigger. So this equation implies that increasing h will increase capital D. What would happen if we increase little g while holding the other givens constant? Little g is on the bottom of this fraction. So if we increase little g, that will increase the bottom of the fraction. Making the bottom of a fraction bigger makes the fraction as a whole smaller. So this equation implies that if we increase little g, that will decrease capital D. So this equation implies that increasing v0 will increase capital D, increasing h will increase capital D, and increasing little g will decrease capital D. Do these results make sense? Remember that capital D stands for the horizontal distance that the motorcycle travels before it hits the ground. The symbol v sub naught, written without an arrow on top, stands for the motorcycle's initial speed. Suppose the height of the ramp is held constant. Because the motorcycle's initial velocity is horizontal, the motorcycle's horizontal speed throughout its trajectory will equal its initial speed when it leaves the ramp. So, if we increase the initial speed, we increase the horizontal speed. If the motorcycle is moving with a greater horizontal speed, then it makes sense that the motorcycle will travel a greater horizontal distance. So, yes, it does make sense that increasing v0 will increase capital D. Remember that h stands for the height of the ramp. Suppose the motorcycle's initial speed is held constant. If the height of the ramp is increased, then it will take more time for the motorcycle to hit the ground. If more time elapses before the motorcycle hits the ground, then it makes sense that the motorcycle will travel a greater horizontal distance before it hits the ground. So yes, it does make sense that increasing h will increase capital D. Remember that little g stands for the magnitude of the acceleration due to gravity. Little g is usually considered to be a physical constant, so how could we increase little g? The answer is that we can change little g by redoing the experiment on a different planet. If we redo this experiment on a planet with stronger gravity than the Earth, then on that planet the motorcycle will experience a larger little g. Suppose we redo this experiment on a planet with stronger gravity, while holding v sub naught and h constant. Because of the stronger gravity, it will take less time for the motorcycle to be pulled down to the ground. Because it spends less time flying above the ground, it makes sense that the motorcycle will cover a smaller horizontal distance. So, yes, it does make sense that increasing little g will decrease capital D. We can also say that decreasing little g, while holding the other givens constant, will increase capital D. You could decrease little g by, say, redoing the experiment on the moon, which has weaker gravity than the Earth does. So, if you're a motorcyclist who wants to make a very long-distance jump, our equation tells us that there are 3 ways for you to achieve your goal. You could drive off a ramp with a very high initial speed, or you could drive off a very high ramp, or you could drive off a ramp on the moon. Here's another issue that you might want to think about on your own. Now let's do a recap of our work on this problem. To succeed with physics, think in terms of components. we had to break the motorcycle's initial velocity into components. Because the motorcycle jumps off a horizontal ramp, the motorcycle's initial velocity is horizontal. Because the initial velocity is horizontal, the initial vertical velocity is 0. And the magnitude of the motorcycle's horizontal velocity throughout the jump is equal to the motorcycle's initial speed, which is represented by the symbol v sub naught, written without an arrow on top. For a symbolic problem, you should write down a list of the given symbols. Symbols that are explicitly mentioned in the problem, like v sub naught and h, are treated as givens. Exception: a symbol that represents what the question is asking you to determine, like capital D, is not treated as a given, even if the symbol is explicitly mentioned in the problem. A symbol that's not explicitly mentioned in the problem is not treated as a given. Exception: a physical constant, like little g, is treated as a given, even if it's not explicitly mentioned in the problem. Why is it helpful for us to write down this list of givens? The list of given symbols is helpful because the given symbols are treated as knowns. So the symbols that are not on our list of givens will be treated as unknowns. Another reason our list of givens is helpful is that only symbols that are treated as givens should be included in our final answer. Because this problem is symbolic, we represented the magnitude of a sub y with the symbol little g, rather than with the number 9.8 meters per second squared. The symbol little g, written without an arrow on top, stands only for the magnitude of the acceleration due to gravity. So when we write a sub y, it's crucial for us to include this negative sign to indicate that for projectile motion, a sub y points downward. To get delta t by itself in this equation, we had to remove the 1/2 and the little g from the left side of the equation. The most efficient way to do that is to multiply both sides of the equation by the reciprocal of 1/2 and by the reciprocal of little g. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge at my Patreon page. You can visit my Patreon page by clicking the link on the screen or by using the link in the video description box. Thank you.